Hello, thank you for being here. My name is Bryan Stearns. I'm presenting my paper titled Toward Unifying Cognitive Architecture and Neural Task Set Theories. I'm not going to be able to go into all the details of my work in this talk. I'll have to look at the paper if you want more info, but I'll try to give the high-level details as best I can. So the goal of this research was to make a single model that could do many different tasks and be a decent model of human learning and transfer. So specifically, I'm looking at three particular tasks: the text editor's task, for using a word processor or the like, and mental arithmetic task for just doing number crunching in your head, and the Stroop task where you need to say the color of a word rather than the text of the word. So in this case you want to say the word green, not yellow. I want to make a single model that can do all three of these, so I will explain each of these three particular tasks in more detail because I will be using these to evaluate my work. So first is the editor's task. This was an experiment back in the 80s with human typists who had not experienced computer text editors before. They were set in front of three different editors and given written edit directions to enter into these editors. And without going into the details too much, you can see this plot how humans got steadily faster and faster with practice over the course of 6 days. Now, these vertical dashed lines show where the subjects transferred from one editor to another every 2 days. And the thing to notice from this result was that the humans did not have significant spikes in taking longer when they switched to a new editor. There was a significant transfer from one to the other, and so the learning curve stayed fairly smooth. And this was a significant result, and we will want to be able to replicate this in our model. Another task is the mental arithmetic task. This was a bit simpler of a task. Subjects were given an algorithm to memorize, such as the one in this box here, and then several different repeated trials of different inputs to operate on with this algorithm. And here on the plot on the right you can see a classic power law learning curve as subjects got faster and faster with practice. Now, after practicing 50 trials of that first algorithm, subjects were given a new algorithm that was different to practice with repeated trials. On the right, these are two average data points of that transfer case. Don't worry about the details of that. For this talk, we're going to focus on that first training learning curve, and specifically notice the time scale of this task compared to the editor's task. Here we're on the order of 10 to 2 seconds, whereas with the editor's task we're on the order of 100 to 20 seconds. So there's an order of magnitude difference between the complexities of the editor's task and the mental arithmetic task. And so this will provide some scope of variety for our single model that needs to be able to do all of these tasks. And finally, there's the Stroop task that I'm looking at, where subject has to say the color of the word and not the word itself. The Stroop effect is well known in psychology, where it takes humans longer to answer when the word and the color mismatch than when they match. And we can measure working memory interference as the difference in latency between when there's a match and a mismatch. Now, Chain and Morrison did a study where they showed that you can actually reduce this working memory interference by training in working memory span, such as memorizing a list of numbers or letters. And they showed they got a significant result where this training did reduce interference by quite a bit. So we want to be able to replicate that behavior too in our model. Now, as it turns out, there is in cognitive architecture research a model that already exists that can do all three of these tasks. It is called Actransfer. It is based on the ACT-R architecture. The way it works is it takes declarative instructions about the task into this same single model, and then it follows those instructions, practices them over and over again, and compiles procedural production rules which allow it to get faster and faster. And the way it compiles those production rules with practice allows it to display a transfer profile similar to humans. So you can see here for the editor's task, the transfer trends that Actransfer displays are the same as shown by humans, and this was a significant result. And if we dig into this model, we'll notice that its results rely heavily on the specific formula from ACT-R for declarative memory retrievals. Shown here is T-retrieve, which is based on two main factors: the activation of a retrieved declarative memory, and F sub R, which is this task-specific latency scaling factor. And you'll notice here for the editor's task, if you remove the amount of behavioral time that's contributed by this formula, T-retrieve, the behavioral profile becomes very flat and closer to 20 seconds. Similarly, if you look at The Stroop model from Actransfer, first, its performance is very similar as far as the overall trends go to what humans achieve, but it is also heavily dependent on this formula t-retrieve because interference is measured using activation. If there is no interference in the stimuli, if the color and the text match, then that increases the activation for retrieving the correct answer. Whereas if there is a mismatch, then the activation is not as high and it takes longer to retrieve the correct answer according to this formula. And now we'll also notice that compared between the editors and the arithmetic model, there is an order of magnitude difference in this scaling parameter f sub r, which also corresponds to that order of magnitude difference between the scales of the tasks between 100 seconds or 10 seconds. So at this point we're beginning to wonder maybe there's something missing here in this model. Now if we look under the hood, we'll notice that this might be because retrieval in Actransfer is also the fundamental decision-making operation, which is to say that the model will do whichever instructions are retrieved first from declarative memory, which is going to be based on activation. If there were multiple rules in long-term memory that could apply at once, for example, if there was a rule that said if A or B, then choose A, or there was another rule known in long-term memory, if A or B, choose B, whichever one of these options is going to be chosen is going to depend on which one has higher activation and which is going to be retrieved into working memory. So you can't have multiple choices in working memory for the model to reason over at once. My hypothesis is that one can take task sets from Neuroscience and model these as an alternative to the retrieve formula. And I'm going to use the Soar cognitive architecture as the basis for this model, and I'm making a new model that is called Prop 3. This is Perimeter Operators Model, version 3. It uses the same general procedural learning theory as Actransfer, but a different decision-making theory for making it run. So first, what are task sets? This is an activity you can do on the other side of your screen. If you see an odd number appear in this box on the right, then you may raise your left hand. Whereas if you see an even number appear, then you raise your right hand. Okay, here's a number. Raise one of your hands. Here's another number. Raise another hand. And final number, raise a hand. Okay. So your neural encoding of those two rules that you had in your short-term memory, that's your task set. You were able to hear my instructions of those two rules and immediately have a representation in your head that allowed you to carry out those operations. This is specifically something that's been observed in the prefrontal cortex that configures stimulus response mappings for tasks. It's short-term, and it's described usually in terms of condition-action rules. Task sets have been observed to be hierarchically arranged in the prefrontal cortex with a rostrocaudal gradient, and a significant property of task sets is that it takes time to switch task sets. You need time to change the activity of your neurons in your prefrontal cortex. So you can observe that if you don't give much time between when someone knows what task they're supposed to do and the time that they're supposed to do it, then it will take them longer to actually be able to perform the task because it takes time to configure the stimulus response mappings for that task. And now let's switch gears and look over at the Soar cognitive architecture. And why do I want to use this to model task sets? Well, Soar is based on using a hierarchy of problem spaces, which in Soar are called goals and sub-goals. So for example, let's say we have a transcribed text task, similar to like a text editor's task, where there's text given on a prompt that you have to type into your computer editor. You can divide this task into goals and sub-goals. For example, transcribed text has sub-goal of first getting the text and then writing the text. Getting the text involves finding the prompt and then reading the prompt. Writing the text involves placing your cursor in the right spot and then typing the word, and so on. You just subdivide each of these goals into sub-goals. So in Soar, there are a set of what's called operators, or decision-making, per problem space. So the get text problem space involves two possible decisions, finding the prompt and then reading the prompt. In Soar, it takes time to change what the active problem space is, what the goal is. This extra time for switching goals would imply something about the cognitive model too, that it would take extra time to switch between task sets. So I'm going to make a model that explicitly reflects this property of task sets in Soar. So in the Prop 3 model, I represent a task set specifically as a working memory structure, which I call a procedure context. This is retrieved into working memory for each goal change, about 150 milliseconds per retrieval based on just how Soar processes decisions and retrievals. And the procedure context instructs the set of stimulus response rules for a goal, for a task. Not just a single option, but a set of options, such as both find prompt or read prompt if get text was retrieved into working memory. And then based on what's loaded into memory, then the model responds to it, follows the instructions, and learns with practice, just as Actransfer does. There were goals in Actransfer too, but they didn't account for extra time. But the editor's task used a very deep hierarchy of goals, such as edit line and then find the prompt for that particular line, and then read that prompt, and then place the cursor, etc. There's a lot of subsequent goals that need to happen. Whereas for the arithmetic task, it's fairly shallow goal stack. There's just step 1, add A plus B. Step 2, divide C with D, and so on. It's very flat. And so one would predict, just from this aspect of the Actransfer models, that the editor's task ought to take a lot longer than the arithmetic task, because it requires more goal switching. So to test this model, I used the exact same model designs that were used for Actransfer. Those are available online. I import those into Soar. I use the exact same goal changes to define my changes in procedure context that I load into working memory. The main difference here is that goal changes take time now, which they didn't in Actransfer. And here's the main result for both the editors and the arithmetic model. You'll notice that using this common 150 milliseconds per goal change, the results are basically the same order of magnitude now as were for the original Actransfer results. This is without using any kind of T-retrieve formula to add extra time to the models. For the Stroop model, interference, instead of being a matter of activation, is a matter of changing goals. The default response of saying the text rather than the color of a word, that's a goal that is immediately available from the general task state. But in order to say the color, that requires extra switches in goal, which takes longer. However, with working memory training, the subject can learn to enter a preparatory goal before the prompt is shown, which allows a faster access to the correct procedure when the prompt is shown. And this results in a performance that is fairly similar to humans also. Slightly different than Actransfer, but they're both similar and show the same trends. Now, there are several implications of the procedure context design using Soar and the model that I've talked about here. One is that a procedure context defines procedural learning for the model. It instructs what to practice. Another is that it defines transfer for the model. This structure and hierarchy within declarative memory is also the structure of what gets transferred across different tasks. It also defines decision making, because a single procedure context structure in working memory has all of the options that the model can choose from and actually think about in working memory. And it also defines task switching, because the time to retrieve a procedure context into working memory defines the time to change context or to switch task sets. So now, what are some of the implications of this work overall? Well, T-retrieve has a long history of successful modeling in cognitive architecture research, in ACTR specifically, and it's supposed to model declarative knowledge retrievals. But now, task sets do not represent a classic declarative knowledge. In a cognitive architecture, they are represented as declarative knowledge because they are in working memory, but task sets specifically have been called a form of procedural working memory. But the implications of this work would be that T-retrieve should not be used to time decision-making specifically. It's great, perhaps, for modeling declarative knowledge retrievals, more like facts about the world, like the sky is blue, but maybe not so great for modeling the loading of decision-making options and choices. Now, future work should perhaps explore the declarative counterpart to a task set, which is called a memory set, which is theorized to be a representation for that kind of declarative knowledge that T-retrieve is normally used to represent. Another thing to point out is that 150 milliseconds per goal change is likely oversimplistic as a model, but for basic modeling, it does work. That's the takeaway from this result. And it is a task general approach to time, and overall, Prop 3 provides a single computational approach using procedure contexts for procedural learning, transfer, decision-making, and task switching, and it aligns the findings from cognitive architecture and neuroscience research into a single system, which models all tasks. So this is a simple initial model right now. There is exciting future work, though, for building on this idea and unifying these two lines of research. There are references for this presentation and my contact info at the bottom. Thank you for your time. It's time to head to questions.